Hello everyone, this is Wang from the University of Hong Kong. Today, I would like to share our work on shape sensing for software robotics. Instead of just measuring the robotic position or rotation, our work mainly focuses on sensing the global robot shape. To measure the global information, there are some research using a grid of sensing units like maps to get the local information. Then combine the local information together to estimate the global shape of the whole body. Our solution is to reduce the number of sensing units by taking advantage of a machine learning method, find the mapping from the local information to the global morphology. In this work, we use the fiber backgrading to capture strain changes. Here shows an example of a single core FBG fiber wrapped helically on a continuum robot. Since one fiber can contain many FBG sensing units, each of them can react with the local change of strain or deformation by reflecting a wavelength shift signal. As you can see from the video, here is a finite element analysis for the robot and the fiber response. The FBG feedback can uniquely reflect the status of the robot configuration. This video shows an example of the software robot configuration sensing in real time. We used a learning-based FBG model for the robot shape prediction. As shown on the left, the shape sensing here helps to improve the control performance. And a 2D image mosaicing was also demonstrated in real time. We can see that when there is an external disturbance on the robot body, the FBG shape sensing can even reflect the robot vibration accurately. Now we can see that computational mechanics, we can see FEA, can help to do pre-analysis at the early stage for the robot design, guiding us to adhere the fiber properly. Also, in some other works, computational mechanics is used to do model initialization for some software robots. FEA are usually used in software robotics field as they can take geometric and material properties into consideration. So it could provide enough noise-free data for analysis or for model training. But the problem is that the FEA process is usually time-consuming. So it could not be directly used in a real-time robotic system. Here we try to combine the advantages of computational mechanics method and machine learning to realize a real-time shape sensing frame for irregular shape or large-scale robot. This is a prototype of A4-sized sensor. We make use of a piece of 1 mm thick rubber sheet and a FBG fiber. The fiber is attached on the surface of the silicon rubber sheet in a dog bone shape to increase its sensibility to different deformation patterns. The work is to find the mapping between the local strain information we see the FBG data and the global morphology change. Where for a large-scale sensor or an irregular shape robot, how to represent the morphology of the shape? The most intuitive way is to use a number of nodes on the body to represent the shape or morphology. But how to get the surface information for a data-driven method? We see the ground truth. If the number of the nodes is very large, it's quite difficult to just use a motion capture system or EM tracking system to get the nodes information. Here, our strategy is to use computational mechanics to enrich the data for training. This means we only need to get the ground truth for several k nodes and regenerate more nodes with FEA. This node data can be used for data-driven method. In case of this A4 sensor, we just measure the nodes of 9 nodes and then generate 77 nodes data for model training. Here is the sensing performance of the A4 sensor. We show that the shape sensor responds accurately to different external stimulation, such as the hands-on deformation or the impact from a water jet, the small bullets. The sensing accuracy was tested by comparing with ground truth. It can be seen from the figure that around 90% of the displacement error are less than 5 mm. Also, we evaluated the long-term sensing repeatability by bending the sensor over 1,000 repeated bending cycles. The result suggests that the sensing was still promising, with stable and reliable response. We also fabricated another mandatory-like sensor and tested it underwater. Still, we got our training data in air, where we manually bend the air fins for full-featured configuration. Real-time reconstruction was accurate, even it was displaced by the hydrodynamic force. This demonstration gave us confidence in the integration of computational mechanics and machine learning. And we see some opportunities in various applications, such as marine robotics or proprioceptive wearables, which will envision great changes in intelligent sensing. So that's all I want to share with you. Thank you.